Hi, this is Dr. Lesher, and this video is on limiting reactants and how to approach limiting reactant problems. So I used the bike example in class today. In this picture, we don't have enough wheels for these 4 bike frames. And this is a really common situation that we run into when we're starting off with say, 2 masses of 2 reactants. One is going to dictate how much of the product can be produced. So let's look at an example of a chemical reaction now. We have here nitrogen reacting with hydrogen to produce ammonia. And if we have to start out with, say, 4 molecules of nitrogen and 6 molecules of hydrogen, that's not fitting our 1:3 ratio that is the ideal stoichiometric ratio for this reaction. So let's just take apart these molecules and see what we can make. Starting out with our ammonia molecules, I've got each molecule has 1 nitrogen and 3 hydrogens. So I can build a few of these molecules, 1, 2, 3. By my 4th one here, I've got a total of 12 hydrogens, which is the amount of hydrogen atoms that I started with here. So by this 4th ammonia molecule, I've used up 12 hydrogen atoms, and I've only used up 4 of my nitrogens. I started out with a total of 8 nitrogen atoms in 4 diatomic molecules, and that means I still have some left over. So in this case, the hydrogen is my limiting reactant. And I can really, those 3 hydrogen molecules can really, or sorry, the 6 hydrogen molecules can really only make 4 ammonias. So how do we, it kind of makes sense when you look at pictures of molecules. And this scales up to the molar amounts, but how do you approach a problem when you're given, say, just a couple of masses or just a couple of amounts of our reactants? So the first step is that you have to have the amounts of reactants in moles. So if they're given to you in moles, great. If not, you have to get them to moles. So once they're in moles, you have to divide each of those molar amounts by that reactant's coefficient. And then whatever has the smallest value, that's your limiting reactant. So that division is taking into consideration that required ratio. In the case of nitrogen to hydrogen, it's 1:3. If your values of these reactants are given to you as masses in grams, you need to do something, right? You need to get those into moles first. Once we've got it figured out as to what is our limiting reactant, that we need a way to sort of organize ourselves. And so I use a table to organize my numbers in this type of problem. And we call these ICE tables. But let's think about this ICE table with the situation we looked at first, this first example here. So the initial line, that has our molar amounts of our reactions and products. Typically, we don't have any product to start out with in a situation, in a problem. In this problem, we had 4 nitrogens and 6 hydrogens. So next step was figure out which is the limiting reactant. If we take these amounts and divide by the coefficients, 4 divided by 1 gives us 4. And 6 divided by 3 gives us 2. So that tells us that the hydrogen is the limiting reactant here. So the next line is our change line. We've already defined the limiting reactant as the one that gets used up completely. So we know that this hydrogen here is going to go to 0. The question is, how are these other reactants and products going to change in terms of their molar amount? To calculate that change, we apply that stoichiometric ratio. So I'm going to work this out for the next example problem in this video. But just looking at our ratios here, for every 1 mole of nitrogen, there's 3 moles of hydrogen. And that means if 6 moles of hydrogen are reacting, that's going to require 1/3 the amount of nitrogen, or 2. And then for every 3 moles of hydrogen that gets used, 2 moles of ammonia are created. So we're going to take that 6 moles of hydrogen and multiply it by 2 moles of ammonia per 3 moles of hydrogen, or 2/3. And so that molar amount of ammonia is going to be increasing, since it's a product, by 6 moles. Then the last line here is the final amounts of the reactions and products. And so this is simply the sum of the initial amount and the change. Reactants molar amount should always be decreasing, so 4 minus 2 is 2, 6 minus 6 is 0, and then product should be increasing. So we went from 0 to and adding 4 moles of ammonia to give us 4 total moles of ammonia. This slide basically summarizes everything I said on the previous slide. So I'll allow you to pause and read more carefully if you need to. But let's move on to a more complex example. So here we have 12 grams of nitrogen, 1.59 grams of hydrogen. And the question is, what's the limiting reactant? And then which reactant is in excess and by how much, and how many grams of the product are produced? So step 1, get all the reactants into molar amounts. We were given masses, and so we need to do our typical molar mass conversions that we've been working on. The 12 grams of nitrogen, that relates to 0.428 moles of nitrogen. And the 1.59 grams of hydrogen, that's actually 0.789 moles of hydrogen. It's a lighter element, so less mass can be more moles. Step 2 is to divide these molar amounts by the coefficients of those reactants. And this is getting at the need for a 1:3 ratio in this case. So the 0.428 moles divided by 1 is still 0.428, but the hydrogen, 0.789 divided by 3 is 0.263 moles. So the hydrogen is our limiting reactant. There's more of it, molar amounts, but because we need 3 hydrogens for every 1 nitrogen, we would need even more than we have for the nitrogen to be the limiting reactant. So that's an important step moving forward, is that the hydrogens are limiting reactant. So step 3 is to create a nice table. Now the first line is pretty straightforward. That first line is our initial amounts, and so that's what we just calculated in the previous slide. 0.428 moles of nitrogen, 0.789 moles of hydrogen. The problem didn't say anything about ammonia in the starting amount of ammonia, so that's 0. Step 4 is to use the molar amount of the limiting reactant to calculate just exactly how much of the excess reactant will be used. So we have 0.428 moles, it's not all going to be used. And also to calculate how much of the product will be produced. So we do this with a stoichiometric ratio. The hydrogens are limiting reactant, 0.789 moles of it, and for every 3 moles of hydrogen, we use 1 mole of nitrogen. So that gives us 0.263 moles of nitrogen that are actually used. So that's what's going to go in that middle line there. And then for the product, we start with that same hydrogen and apply a stoichiometric ratio to calculate how much ammonia is going to be produced. And we get 0.526 moles. So these values go in the change line. I have a negative sign on the nitrogen because that amount is being used up. So the overall number of moles of nitrogen will be decreasing. The limiting reactant, the hydrogen, all of it will be used up. That's the definition of a limiting reactant. And then the ammonia has a plus sign because this is actually being produced. Then step 5 is to calculate the final line. And here we're just adding together the first 2 lines. So 0.428 minus 0.263 gives us an excess of 0.165 moles of nitrogen. The limiting reactant should go to 0, and then the 0.526 is how many moles of the product I have. So step 6 is look back to your problem and see how you need to express the requested values. The excess reactant, we have 0.165 moles of it left over, but we need to express that as grams. So another molar mass conversion, we've got grams. And then for the product, we also want grams of product. So another molar mass conversion, and we calculate that we have 8.96 grams of ammonia. Well, I hope that was helpful, and we'll do more of these in class.